Should I start or should we wait? Okay. So hello and welcome to the third lecture in the course on category theory for the summer school. The topics today are what I call universal constructions, which I'll explain in a second. And in particular, the ones we need to describe a Cartesian closed category, which is the kind of category we need in order to interpret the simply typed lambda calculus. So this is kind of the plan and the sort of the reason for the plan. And this topic could easily take a week or even more, but I don't have a week for it. I have a day. So I'm going to try to give you an overview and spend the time on sort of the important parts that are like nuts and bolts for understanding other things. There are some things that are important to understand that there just isn't time to explain. So please, especially for today's lecture, have a look at the notes because they'll clarify a lot of the things that I just don't have time to go into detail on during the talk. Okay, so I guess the place to start is what is a universal construction? So different people use this phrase to mean different things. I will use it in the following way. By a universal construction, I mean a construction within a particular category of some particular shape, and I'll expand on that, what that means in a second, which characterizes it uniquely up to a canonical isomorphism with respect to constructions of the same shape in the same category. Okay, so that probably sounds exceedingly vague, but hopefully, once you see a couple of examples, you'll see what's going on. And then the punchline comes tomorrow when we see that if we look at the two-dimensional structure of categories, that we can describe all of these as instances of one thing that lives in a higher dimension, basically. Okay, so today it's basically examples and the examples that we need to define Cartesian closed categories and understand how we might interpret the simply typed lambda calculus, and then tomorrow we'll generalize. Okay, so by way of motivation, in the category of sets, it's the case that if you have a singleton set, then for any other set, there's just a single function from that other set to the singleton set, right? Namely, the function, the constant function that takes the only possible value because there's only one thing in the singleton set. So this gives us a behavioral characterization of a singleton set in the category of sets. Do you see that? We just used some things about the maps, which are the functions. So if we generalize this idea to an arbitrary category, we get our first universal construction, which is called a terminal object. So a terminal object is a distinguished object of a category, which I'll call T, the object, not the category. Such that for any object of the category, which I'll call X, you should think of this as the distinguished thing, and this is like the probe thing. There is a unique arrow, which I'll call little x, going from the probe thing to the distinguished thing. Okay, so this is just like what I just described in sets. You can think of this singleton set, this as being any other set, and the unique map as being the constant function that takes the only possible value. Okay? So typically we call this unique map by the name, well, I say bang, and I write it as an exclamation point. The exclamation point is pretty common. I'm not sure what other people say when they speak this out loud. Okay? But this is the property. And remember, when I was using the dotted arrow, I was asserting that something exists, and usually uniquely, but I'll use words to clarify that. Okay? So do you see how this is just taking the characterization of a singleton set that we just gave and generalizing it to an arbitrary category. Okay, so another thing that we learned yesterday, right, was whenever we have a construction in a category, we can flip the switch by getting out our red pen of duality and make the dual construction. So what should be the dual construction? Well, that's called an initial object. Okay, and it's an object in a category, okay, and the dual of an object is just an object, right? Such that for any other object in the category, again, just an object, there's a unique map, excuse me, going from the probe thing to the distinguished thing. Now remember, in the opposite category, the domains and codomains of all the arrows are reversed, so this time we get a unique map going from the distinguished thing to the probe thing. So we reverse the map, and we also reverse the exclamation point, and I write it like this, and I pronounce that co-bang. It's the upside down exclamation point. Okay? And so for free, we get an initial object. Okay. So I think what I want to tell you about next is philosophy. Right. So there was this guy, let me use the other half of this board, named Socrates. And he was a Greek philosopher. And among other things, he, at least according to Plato, used to go around telling people that they should know themselves. He would say, "Know thyself." And I'm not sure if people understood what he meant by this, but presumably it was good advice. And it's good advice in life, and probably also good advice in category theory. So what I mean is that whenever we have a universal construction, right, we said that it's something, in this case just an object, but later it will be something more fancy, such that for any other thing that is of the same form as that thing, there is some kind of unique relationship between the two. Now, the thing itself certainly has the same form as itself, right? So it should have this unique relationship to itself. Make sense? Okay, so what we mean, or what I mean by this, is that we should, so remember we call this the distinguished thing, and this thing the probe thing. So we should try to probe ourselves, which, okay, that might sound a little weird, but that's what we're going to do. Okay, so what does that mean in this case? It means here we have a terminal object, and as the probe, we pick the terminal object. Okay, so we have the distinguished bang map that goes from the terminal object to itself. But what other map do we know lives in that Hom collection? The identity, right? Okay, but because this is unique, we know that these two maps are equal, right? So we just discovered that the bang map applied to a terminal object is just the identity map on that terminal object. And I'll call this the principle of identity expansion. And whenever we encounter a new universal construction, we're going to go through this process to see what we learn when we try to probe ourselves. Okay, so that's that. The next thing I want to tell you has to do with this uniqueness thing, right? So another lemma, I guess I should have labeled that one a lemma, sorry. And this will again be a recurring pattern as we go, is that in this case we're going to see that terminal objects are unique up to unique isomorphism. We learned what an isomorphism was yesterday. Okay? So let's go through the proof, and as we go, you'll understand what the statement means if you're a little shaky on what it's saying. Okay, so basically we're asserting that something is unique up to something, right? Up to some fudge factor. Okay, so whenever you want to try to prove that something with a special property is unique, a good strategy is to assume that there are two such things and then make them fight. By which I mean, use their special property on each other, and in the process of doing so, you may well discover that the two candidates were the same thing all along. Right? So this I call the principle of proof by Fight Club. And if you don't understand the reference, I could explain it to you, but the first rule of proof by Fight Club prevents me from doing so. So say we have two terminal objects. We have T and R. And they're both terminal. Because R is terminal, there's a unique map from T to R, which I'll call little t. And because T is terminal, there's a unique map from R to T, which I'll call little r. I hope I didn't say the wrong thing there. Okay? But now if I compose these maps, then I get a map from T to T. And that has to be the bang map on T, right? Because that's the only map in that HOM. But what did we just learn by identity expansion? That this is the identity, right? So we just learned that T followed by R is the identity on the object T. Okay? But now the roles of T and R in this scenario are completely symmetric. So if we just switch them, we'll see that the arrow R followed by the arrow T is the identity map on the object R. Sorry about that. Okay, so what does that tell us about these two maps? So yesterday we learned what an isomorphism was, and I don't remember, but I hope I said, I used the vocabulary that if you have an isomorphism, then the other thing, the other map involved in its thing is its inverse, right? So we know that R and T are inverses of each other. They're two-sided inverses. So in particular, T is iso. Okay, so we're almost done. We just discovered that terminals are unique up to iso. But what about this? I said it's unique. How do we know there's not another one? Well, let's look at the universal property of R being terminal, right? That says that there's only one map in the HOM from T to R. So could there be another iso from T to R other than little t? No, right? It has to be the only one because the whole HOM has exactly one thing in it. So there can't be another isomorphism in it because there's not any other morphism in it at all. Okay? So, and it's the only one. And the only one. Okay, so this pattern is something you're going to see repeated several times today. So this is the simplest instance of it. So if there's anything confusing about this, we should stop and clarify now. I saw a hand go up, so yes?
On the second equation, I'm getting confused with how you got R and T.
Sorry, let me write this non-crazily. Okay, how I got the second equation? Okay, so I kind of took a mental shortcut in that.
Those are just the other
Yeah.
maps that go back.
So T and R have exactly the same property as each other, namely they're both terminal, right?
Yeah.
So I drew the diagram that explains why this is true. But if you take this diagram and you swap the labels T and R, then you'll see that this is true. Okay? Good. Anything else? Yes?
So you're not claiming that T and R are the same, right?
I mean, they can't be the same. Wait, okay, elaborate your question.
Necessarily the same, right?
So the objects T and R or the arrows T and R?
The objects.
Okay, I don't know that they're the same object up to identity, but I know they're the same up to isomorphism, and even better, unique isomorphism. So in a category, that's about as good as you can do, right? Because as we go, we're going to describe things by their properties. And if two things have exactly the same properties, then there's nothing you can do to tell them apart, basically, right? So in a category, being unique up to unique structure-preserving isomorphism is like the gold standard. That's as good as you're ever going to be able to do. Okay? Okay. So let me just tell you briefly some terminal and initial objects in. So in sets, we just saw what a terminal object was. It was a singleton set. And any guess what the initial object is? Well, okay, I'll let you think about it, but I'll just tell you it's the empty set. And you should convince yourself of that maybe during the exercise session. In categories of categories, and for simplicity, we'll just stick to small here, right? It's the same thing. The singleton category, well, okay, it's not the same thing insofar as it's not the singleton set, but it's the singleton category that we met on Monday, right? Remember that? One object, one loop is terminal. And the empty category, which we also met on Monday, is initial. And so now I'm going to leave you, I think in the notes I wrote this, but there's an exercise in the category of preorders. You should figure it out. And in a preordered set as a category, you should figure it out. So a preorder category from Monday, you should figure it out. Okay? Okay, so I think that's what I want to say about that, except now I can tell you about how to interpret the unit type. Okay, so I will call the unit type, I'll write it like this, like with the top symbol. I'm not sure, I don't know if that's what other people use, but we'll just stick to it for now because it's quick to write. We can interpret that as any terminal object in the category. And if you remember the introduction rule for it, it says that in any context, there is, well, I don't know what I'm going to call it star. I don't know what other people call it. In any context, there's a distinguished element, in fact, the only element, in this type, right? And we can interpret this term in context. So remember from the first day, the interpretation of a term in context should be a morphism from the interpretation of the context to the interpretation of its type. So this has to be something that goes from the interpretation of gamma to, well, the interpretation of this, which is this, which I'll just write. Okay, but what can I put here? What's the only thing that lives there? It's the bang map on the interpretation of gamma. Okay. We can also now understand how to interpret an empty context. And we do that basically the same way. We just interpret, I'm not sure how to write it, I'll write it like the empty set because otherwise there's nothing to write. This is also interpreted as some terminal object. Okay? And the reason for that is basically some term is well typed in the empty context just in case it's well typed in a singleton context whose only variable is of unit type because there's no elimination rule for the unit type, so it doesn't tell us anything. Okay. So, any questions about that? Okay. Let's see. I will leave that and erase this. So going back to sets for inspiration, it's also the case that for any element of a set, there's a bijection between, well, the collection of elements of the set, which is just the set, and functions from a singleton set to the set, which send the only inhabitant of the singleton set to that thing, right? So for every element of the set X, there's a function that sends the only element of the singleton set to X. You can think of these functions as like surrogates for these elements, right? Now, in categories, our objects aren't sets, so they don't have elements like this, right? But they can still have these surrogate maps as long as we have a terminal object. So this brings us to the idea of what's called a global element. And this is also known as a point. And this is any map from a terminal object to some object in a category, right? So another way to say this, well, no, actually, that's I guess the only way to say this, right? It's any map whose domain is a terminal object, right? So do you see how this is just the category version of this? Okay, these are the like surrogate functions for the points, functions, surrogate maps for the points, but there are no real points. We just have the maps. Okay, in contrast, we can have what's called a generalized element. And that is any arrow into, okay, so a generalized element of X, let me say, of X, is any map from anything else. Oh, okay, let me say it this way. Arrow in whatever category, such that the codomain of that arrow is X. So do you remember yesterday we came up with another way to say this? It's an object in the slice category of C over X, an arrow into X. Okay? So if we, well, okay, I'm not quite done talking about context, but we can think of these as terms in an empty context, and these as like representing terms in an arbitrary context, right? Because the domain of the arrow is completely unconstrained. Okay, and now to cash a check that Bob wrote for me on the first day, we say a category is called well-pointed if the points, that is the global elements, are sufficient to distinguish parallel maps. So let me write this out in symbols and then say it in words. If for any parallel maps, say F and G in the category, if for all the points okay, so I have to line wrap here. This implies that the maps are equal. Okay, so this is saying, this is like the function extensionality in set. Remember that function extensionality in set said that if two functions agree on all points, then they're the same. And this is just saying the same thing, except it's using this notion of point, namely a global element. So it's saying if two maps agree on all the global elements, then they must have been the same to begin with. Okay, and this becomes relevant in type theory because in many instances the way you define equality is you define equality on terms in an empty context, and then you define equality of terms in an arbitrary context by quantifying over all closing substitutions. And quantifying over all closing substitutions just means precomposing with points, with global elements. So in a certain way, this is saying that a certain model will be well pointed if that's our notion of equality. But I can't go into too much detail about that. Okay, so yes. Yeah. Oh, did I not say that? Okay, sorry, I can't remember. But if I didn't say that, one is the notation I will use for an arbitrary terminal object. And you say, well, what if there are two different ones or something like that? And in the end, it doesn't matter insofar as they're as similar as they could possibly be. They're related by a unique isomorphism. So yeah, sorry, I apologize if I skipped that.
So obviously here we have a terminal object. Do we always have a terminal object?
No, not every category has a terminal object. But when it does, then it has all these properties. So for those of you who keep coming up to me and asking me what is category theory good for, I'll say, well, here's an example. You know it if you have something in whatever you're studying that's a terminal object, then you know some facts about it just because it's a terminal object, regardless of what else you may know about it. Okay, so I'll move on to the next universal construction. Okay, I'll just erase this. I thought I could be clever and reuse it, but it's probably more trouble than it's worth. Oh boy, okay. The next thing I want to tell you about is products. Of objects. So I'm deliberately doing these universal constructions in a very methodical way because I want to show you the way in which they're similar. Okay? So a product of objects A and B, say, is a span on A and B. And of course, I have to tell you what that is. So that is an object and two arrows coming out of it, one going to A and the other going to B. So I'll call these little p0 and little p1. Okay, so that's a span. You can think of it as like a little bridge or something. Such that for any span on A and B, so what that is it's another thing of the same shape. Right? So a span is a pair of co-initial arrows, if you want to say it in a fancy way. It's another span. Okay, so this is the distinguished one. This is the probe one. There is a unique mediating arrow, which I'll write T, going from the vertex of the probe thing to the vertex of the distinguished thing, such that the following diagram commutes. So here is the distinguished thing with its projections. Oh, I used a word I haven't defined yet, sorry. Okay, so here is the distinguished span. Here is the probe span. Here is the map I'm asserting exists, going from the vertex of the probe to the vertex of the distinguished. And then the property that this map has to satisfy is that it makes these two triangles commute. So T followed by one leg of the distinguished span is equal to the analogous leg of the probe span. Got it? Does it make sense? Okay, so let's introduce a little bit of vocabulary here. First of all, so here's vocabulary. The A and B are called the factors of the product. The legs of the distinguished span are called projections. And we write them generically using the Greek letter pi, or also p, but I'll just say pi to distinguish it from this p. Right? T, the mediating map, is called the tuple. Of the probe span legs, x0 and x1 in this case, and we write that in this angle bracket notation, like that. And finally, the P, should have left a little bit more space. Okay, semicolon. P is written oftentimes A cross B because of the uniqueness result we're going to get to momentarily, right? Okay, just like the terminal object I generically refer to as 1, a product object I can generically refer to in this notation. Okay? So I know this is kind of heavy, but the picture is what's important. So it says it's a this thing such that for any this thing, which is the same shape, there is a unique map mediating between them such that the diagram commutes. That's what you need to remember. Okay, so now we have a universal construction. We have some work to do. The first thing to do is dualize it. Okay, so the dual of a product is a product in the opposite category, which is called a coproduct. So coproduct of objects. Okay, the dual of an object is just an object. What's the dual of a span? Well, it must be a cospan, whatever that is, right? But we can figure out what that is, because here we have a diagram for it. And the way we translate that to the opposite category is we just reverse the orientation of the arrows, such that for any cospan on the same factors, right there is a unique map T. So in products, it goes from the probe to the distinguished. But of course, we have to reverse it. So in coproduct, it goes from the distinguished to the probe, such that, okay, now to figure out the condition, we have to reverse all of these arrows, such that this diagram commutes, right? And now I guess, I don't know if I'll refer to this later, but just for completeness, I'll say the things here are called the cases of the coproduct. The mediating maps are called, I call them insertions, and write them with iotas. The thing here is called the cotuple, and written with square brackets rather than angle brackets. And the object at the vertex of the cospan is written with an infix plus. Okay, so it's exactly dual. Once you get this duality thing down, as soon as I tell you what a product is, you'll know what a coproduct is. Like there's nothing to know. It's completely mechanical. Okay, so let me see. Right, so we have a universal construction. So the next thing to do is to follow Socrates' dictum and figure out what we know about it by probing it with itself. Okay, so here's our product of A and B with the projections. And the whole point was we wanted the probe span to just be the distinguished one. Okay, and then universal said that there's a unique map here, tuple, making the diagram commute. Now, can you think of a map here between P and P that makes the diagram commute? Right? It's the identity, obviously. Okay, but we just saw that that has to be the tuple of the projections. Oops. So the tuple of the projections is the identity of the product. Make sense? Okay. So that's the identity expansion lemma for products. And now we have the uniqueness thing. So the uniqueness lemma says that products are unique up to a unique, well, some structure preserving iso. What do you think that the structure should be here? Well, let's see. It's going to end up being basically the arrows involved in the distinguished construction. So here, that was the span, right? And the span of a product is the projections. So this will turn out to be projection. Okay? So previously, for the terminal object case, there was nothing to be preserved because the terminal object was just an object. There was no structure. But here, there's some structure. It's this span thing, right? So we have to preserve that structure, which means we have to preserve the projections. Okay, so let's go through that proof quickly. So we want to show that something is unique. So what do? Fight Club, right? Someone said it. Okay, so here, P is a product of A and B with its projections. Let's say Q is another product of A and B with its projections. Okay? Now, because Q is a product, there's a unique tuple here, we'll call S, right? That makes these triangles commute. But now, because P is a product, again, there's a unique arrow here from Q to P, making these triangles commute. Okay? So what do we know? We know S followed by T followed by P0 equals P0. But this triangle commutes, so we know S followed by Q0 equals P0. Wait, that's not what I wanted to say. Let me do this again. We know S followed by T followed by P0 is S followed by Q0, right? Because this triangle commutes, so we can take this shortcut. But that's just P0, because this triangle commutes, so we can take this shortcut. And likewise with the other one, right? So I'll just put here little I, where I ranges over 0 and 1. Okay, so it means if I take this composition and follow it by a projection, then I just get back that projection, right? So that means from this I can infer that S followed by T is the tuple of P0 and P1 for the product P, right? Because I had this thing followed by that is that, right? And so, and likewise on this side. So this thing must be the tuple of these things. But what did we see just a minute ago by identity expansion? This is the identity on P, right? So S followed by T is the identity on P. Again, reversing the roles. So likewise, T followed by S is the identity on Q, right? Just take this diagram, swap all the P's and Q's. Yes?
So it seems like we've gone through kind of a lot of effort to show that S and T compose both ways of identity, but because of the bottom of this diagram, it's just like the top. Is there a reason that you can't just draw T as an arrow going back up from Q to P and immediately conclude that they're an isomorphism since they have to compose the identities of directions?
Well, I mean, that's basically what I'm saying, right? I'm just saying it in slightly longer words. But yes? okay. So my strategy here is to like use the same technique on every universal construction. But yeah, like what you said is true. Okay, so the upshot is that S is an iso. So we're almost done, right? But what's still left to show? It's the unique structure preserving iso. So again, just like last time, we look at the universal property of Q, right? And we see that there's a unique map from P to Q that makes the two that commutes with the respective projections, right? So by the universal property of Q, it's the only one, because Q, a product, it's the only one. Okay, so this is the pattern. I'm sorry if this was a bit like slow and boring for some of you, but I just want to sort of grind it out a couple times so that whenever you see it, you'll be able to follow the pattern. Okay. What's next? Oh, right. Okay, so whenever we have a product of objects, we get a special arrow, right? Because say I have an object A. I always have the identity arrow from A to A. And I have it again, right? But that means that I'm going to stop labeling the projections of a product from now on. You can just infer their labels. Because I have this span, right, over A, which is just two copies of the identity, I get this map here, which is their tuple. Okay? So I always have this map for any object A. And this is called the diagonal map. Which I'll write delta, and it goes, or I should write it like this, excuse me. Delta of A goes from A to A cross A. So what this does, and notice that the property it has, if you follow the diagonal map and then you take a projection, then you just get the identity. But there's two projections you can take, so you can get from A to two copies of A. So it lets you duplicate things. Diagonal maps let you duplicate things. Okay, just like with the bang map of a terminal object, it lets us discard things. It lets us throw things away. So in a category that has products and terminal objects, we can copy things and we can throw things away. And maybe like you didn't even think that this is interesting because maybe you're just used to everything working that way. But there are times when things don't work that way. So there are what are called substructural type theories and substructural logics that don't work this way. There's the entire world of quantum computation, which doesn't work this way, right? You can't copy a qubit. That's the no cloning theorem. That's one of the foundations of quantum computing. So not everything works this way, even though a lot of things that are familiar do. Okay, so let's see. What do I want to do next? Oh, I want to give you an exercise. So explain why the following holds, and I'll draw a diagram to show you what I mean. So if I have an arrow and I compose it with a tuple map, then it's the same thing as if I compose the arrow with each branch of the tuple, right? So here is x A cross B here's the tuple. Okay, so here's the setup, right? I is composable with a tuple of f and g. So here I can make the tuple of the composition, right? This is I followed by f, and this is I followed by g. And because that's a span over the product, I have its tuple, and these maps coincide. So it's not too hard, but you should work through the details. Okay, and then I'll tell you two particular products in important categories. So in set, the set of ordered pairs, which is just what you think it is, right? So it's a set of A and an X, where A comes from the set A, X comes from the set X, and I'll call this, well, okay, I'll just leave this. Well, okay, I'll write it like this. Okay, so you should check that the set of ordered pairs is a product in sets. That's the thing, right? I guess this is continuing under exercise. And then in categories, so let's just stick to the category of small categories to be simple. The category of ordered pairs which I have to define for you, right? So if I have categories, if I have C and D, two categories, then I'm going to form what I call C cross D, right? I'm going to define what this is. So its objects are defined to be ordered pairs of objects from C and D respectively. Okay, and then I guess I should write this all down, but it's everything what you would just expect, right? Its arrows are the arrows where, like pairs of arrows, where the first arrow is an arrow from the first category, and the second arrow is an arrow of the second category. And let me just say, without writing it down, that the identities and the composition are defined point-wise, right? Well, okay, maybe I will write it down because I'll need it in a minute. The identity on the pair A and X is defined to be the pair of arrows, namely the identity on A and the identity on X. And then the composition, if I have an FP pair of arrows, and I compose that with a G Q pair of arrows, then that's just the pair of arrow F followed by G, P followed by Q. So it's just what you would imagine, right? If I asked you to make this up, this is what you would make up, I'm sure. Okay, so you should check that these things have the property of being a Cartesian product or a product in the respective categories of sets and small categories. So hang on, let me check something here. Okay. Okay. So one of the things that we try to do in category theory is whenever we have a construction that we can do on objects, we ask if it extends to the arrows as well, right? So I just defined for you in the last few minutes what a product of objects is in a category, right? Namely, it was basically a terminal span, right? And so the question arises, like, can we make a product of arrows? Can we come up with a sensible definition for a product of arrows? Okay, so let's think about this. So say I have an arrow F that goes from X to A, and an arrow G that goes from Y to B. I want to come up with some notion of the arrow F cross G. So first of all, what do you think should be its domain? Okay, a good possibility is that the domain should be X cross Y, and the codomain should be A cross B, right? That seems like it makes sense. So let's put X cross Y and A cross B here, and we know we always have the product projections, which I won't label, but they're always there, right? Okay, so now what do we do? Well, we see that this is a product, right? And it has this property that for any span over its factors, there's a unique mediating map. Now, do you see a span over its factors somewhere in this diagram? If you just compose this projection with this arrow, you get a map to A. And if you compose this projection with this arrow, you get a map to B. And that makes a span over the factors of this product from this vertex, right? So that means that there's a unique mediating map here, namely the tuple pi 0 followed by F, comma, pi 1 followed by G, which makes this square commute. Okay? And this is a good candidate for the definition of the product of arrows, right? Because it has this nice property that it's the unique thing that makes this diagram commute. So let's try that. Okay, so this is our candidate definition for a product of arrows. But now we have an object map for products, right? We know what a product of objects is. And we have an arrow map for products. Well, a candidate one anyway. And remember, this was the ingredients for what a functor is, right? You need an object map and an arrow map, and they have to satisfy two conditions. So the first one was that they have to respect boundaries, right? That was the good office mate condition, but that holds true by construction. And what's the other thing they have to respect? Exactly. So I call that the composition structure, which meant, in particular, the identities and the composition, the binary composition, because then by all the associativity and unitality, it respects all the compositions. So let's see if that works. Okay, so claim this construction, blank cross blank, is a functor whose domain is this category, which I just conveniently defined here. Ooh, that worked out really well. Okay, namely the ordered pair category, right? And whose codomain is the category itself. Okay, so we have to check this. Okay, so let me pause because this notation probably looks totally confusing, right? It looks like there's a cross here and a cross there, and it's not clear what the difference is. This is the ordered pair category. And this is the name of an alleged functor. Well, okay, in a moment it won't be alleged, but okay? So let's see if this works. So what do we have to show? Well, we have to show that, okay, so there's the nullary case and the binary case. For the nullary case, that is the units, the identities, we have to show that the identity on, say, an object A0 and the product of that with the identity on A1 is equal to the identity on the product of objects A0 and A1, right? Because this is the functor image of the identity maps, whereas this is the identity map image of the functor, this is the identity map on the functor image of the objects, right? See how that works? Okay, so if we just draw the diagram, we'll see what's going on. A0, A0, A1, A1. Here's this identity. Here's this identity. Okay, this is, I didn't leave myself enough space, so let me just rewrite this quickly. Sorry. And then the projections. Okay, so what do we have to show? Well, by definition, the left side of this equation, right, is the product of arrows, which is the unique arrow here, which makes these two squares commute. By definition, this is the unique thing here that makes those commute. Okay, does this thing do the job? If I do the identity here and follow it by the projection, then is that the same thing as the projection followed by the identity? Well, yeah, that's just the unit law of composition, right? And then likewise for the other square. Did that make sense? Do I need to label the projections and stuff, or do you get it? Okay. So that case works, right? And now we have to do the composition case. I guess I'll do it over here. So what do we have to show here? Binary case. Okay, so we have to show that, okay, let me draw the diagram because otherwise it's going to be hard to see. So if I have an F0 here from an A0 to a B0 and a G0 from B0 to C0, and likewise over here, I have A1, B1, and C1 with F1 and G1, and then all of the products and all of the projections. Okay? So what I need to show is that if I take the product of F0 compose G0 with F1 compose G1, that is equal to the composition of F0 with G0. Wait, something's wrong. What did I do wrong? F0. So here I did the product of the compositions. Here I need to do the composition of the products. Sorry. F0 cross F1 compose G0 cross G1. Okay. I think that makes sense. Okay. So just like here, right, I did the product of two identity arrows, and then I wanted to see if it was the identity on the product of the objects. Here, I have the product of two compositions, and I want to see if it's equal to the composition of the two products. Okay, well, so what are these arrows here that make the squares commute? This one is F0 cross F1 by definition, right? And likewise, this is G0 cross G1. So this map makes these two squares commute. This map makes these two squares commute. By pasting, I have the left-hand side and the right-hand side commute, right? Now I can compose here to get F1 compose G1, and likewise compose here. Sorry, I didn't leave enough space. F0 compose G0. Okay? And now if I take the product of these two composed maps, that's the unique map from here to here, making the left side and the right side commute, right? By definition. But because of pasting, the composition of this and this, which made this and this commute separately, if I paste those together, it makes the whole left side commute. And likewise, it makes the whole right side commute, right? So this composite has to be the same thing as this map, which was the unique thing making the left and right side commute. Okay, did that make sense? Okay, if at least not totally no, then like think about it offline, and if it doesn't make sense, you can ask me later. But the point is, you just use all of the properties you have at hand, and you see by uniqueness that the things have to coincide. Okay, let me check where I am. Not so good. Okay, so this brings us to the structure that we need to interpret products of types. Okay, so it turns out that if we have a product of types, where this is the product in the language of types, we can interpret that as a product of the objects which interpret the factors of that product of types. Okay, so this is the product in type theory. This is the product object in a category. Okay, let's see why that works. So remember we have the introduction rule for products, which says that if we have a term of type A in some context, if we have a term of type A in some context and a term of type B in that same context, then we have, well, I don't know what notation to use, but we have this term of the product type in the same context, right? So let's see how we can interpret this using the things that we have around for products. Okay, well, whatever this is, it has to be a map from the interpretation of gamma to the interpretation of the product type. But what we have is a map from gamma to the interpretation of the first projection, and a map from gamma to the interpretation of the second projection, or factor, sorry, I should say factor, not projection, right? So we can interpret this to be, this time, the categorical tuple of the respective interpretations. Okay, I know this looks like syntactic mumbo jumbo, but it's just because, well, coincidentally or cleverly, I called the product and the tuple the same thing in the types and in the categories. Okay, and then for the elimination rule, it says, right, in type theory, it says that if we have something of product type, oops, then we can take its projection, and it has the type of the respective factor, right? So if we want to interpret this thing, it should be a map from the interpretation of gamma to the interpretation of A. Well, how can we get such a map? We can take the interpretation of P, whatever that is, which we know goes to the product, and compose it with the projection, right? And likewise for the second. So we just use the structure of the product object in a category to interpret the introduction and elimination forms for the product type in the type theory. Okay. And it turns out that we can do the same thing for context. So I have very little time, so let me just mention this. If I have a context already, and I want to extend it with a new binding, right, then I can interpret this as, remember, this has to be some object now in the category. And this can be whatever the interpretation of the context we're extending is, recursively, right? And take the Cartesian product of the interpretation of the type of the new binding. So you should read more about this in the notes. I'm not going to say more about it now. But the point is, basically, that terminal objects and product types are just what we need to interpret unit types. Did I say that wrong? Okay. Terminal objects and products of objects are just what we need to interpret unit types, product types, and contexts. Okay. So I want to momentarily go back to the unbiased point of view that I mentioned in the first day's lecture and apply it to the product in a category. So remember, on Monday I said that even though we axiomatize categories with identity and composition maps, what's really going on is that we have sort of a length index composition. Any composable configuration of arrows has a composite arrow. And so if we want to apply the same principle to products, we have this idea that maybe we don't just want a terminal object and a binary product, but we want to have sort of n-ary products for any natural number, right? So let's think about what that would be. Okay, so an n-ary product would be an n-ary span. Okay, so here are our n factors, a0 up to, I guess, an minus 1, right? And here are the legs of the span. Okay, so it's an n-legged span, such that for any other n-legged span, there's a unique mediating map from the vertex of the probe to the vertex of the distinguished, making the n triangles commute. Make sense? I'm just generalizing the definition from 2 to n, where I'm letting n range over the natural numbers. Okay, so let's think about what this would be for some small natural numbers. What about if n is 0? Well, then the universal property says that we have an object P with 0 projection maps, such that for any object X with 0 legs of its span, there's a unique arrow from X to P, making all 0 triangles commute. Okay? So that's the universal property of a null-ary product. But we already saw a construction that has the same universal property. What was that? Right. So the null tuple here, which is the universal map, right, is just the bang, and P, well, P up to iso is a terminal object, making the null tuple the bang map. Okay, how about unary? So for this, we have a distinguished object P with one factor, such that for any object X with a unique one-legged span, which is just an arrow to the same factor, there's a unique map from the probe thing to the distinguished thing. Okay, this is the one tuple of X. But what if we just let P be A, right? Then for any map here, we just put the same map there, right? So if we can let P be A. So a one tuple is just a tuple of one factor is just that object, in other words, right? So then the one tuple of X would just be X. Okay? So we have null tuples, one tuples. We already saw two tuples. So nullary products, unary products, binary products. Now, how about for more than two? Okay, well, it turns out that the universal property of, say, three-legged span is the same universal property as the iterated binary case and associated any way you want because products are associative. So I'm about to tell you some stuff that will probably not be surprising, and if you interpret it in a certain light, is stuff that you learned in elementary school. But, oops, it's not a product. Products are associative up to an isomorphism, a unique structure preserving isomorphism, in fact. Okay? Likewise, they're unital with the nullary product being the unit. And they're even commutative or symmetric. Okay? So having finite products is just the same thing as having nullary products, that's a terminal object, and binary products because, well, we saw having unary products you get for free, and for anything greater you can just associate. And all the laws you know about multiplication in arithmetic are true up to isomorphism about products and categories as well. Okay, so a Cartesian category, let me write it up here. So a category that has finite products is called Cartesian. Okay. Having a terminal object and a binary product is the same thing as having all finite products. And a category that has those things, okay, grammatically I've painted myself into a corner, makes a category Cartesian. Okay, and you can dualize all of this stuff to the coproducts. Maybe if you want, you can try that during the exercise session. You can think about what finite coproducts are and what a co-Cartesian category ought to be. So remember I said on the first day that universal constructions, or I didn't use the word universal, I said constructions and their duals can occur in the same category and interact in interesting ways. So that is the case with the product and its dual, the coproduct. And in many cases, we want a certain relationship to hold between them. Okay. What we want, certainly for categories in which we intend to interpret the connectives, the type formers of sum types and void types using the duals of the product and the terminal object, namely the coproduct and the initial object, right? So if we want to do that, then it turns out that we need the following thing to hold. So how to say this? A category is called distributive. If there's an ISO which I'll write like this. Okay, so it says that a category is distributive if there's a map that goes from the product of something with a coproduct to the coproduct of that thing with each of the cases of the coproduct. Okay, so this is something that's certainly true in arithmetic. You learned this in elementary school, I'm sure. It's the reason why the multiplication algorithm that we've all learned as children works, right? If you want to multiply a number by 91, then you multiply it by 90, which we do by multiplying by 9 and then adding a 0, and then multiplying it by 1 and then adding the two together. Right? So this is true of natural numbers. It's not true of every category, but for sort of well-behaved categories that have products and sums, we want it to be true, and those are called distributive categories. So it turns out that this implies, although it's not obvious, let's see, categories there. Okay, this implies that there is an ISO, which I'll call, what did I call it? Oh, ABS. So this is for distributivity. This is for absorption. Okay? So this is how multiplication and addition works in natural numbers. This is how multiplication and zero work in natural numbers. It turns out that they don't automatically work this way in every category with products and sums, but in distributive categories they do. And you should really think of this as the binary case, and this is the nullary case, right? This is saying that the product distributes over the two cases of a sum, and this is saying that the product distributes over the zero cases of an initial object. Okay, so it turns out that there is a construction that is sufficient to guarantee that a category is distributive. And furthermore, we really want that construction because it's what lets us interpret function types, which is the most important type in programming languages, right? So that is the exponential. Let me check my time because I know I'm not doing well here. Okay, I think I'm technically out of time, so I guess I'll stop there and take up exponentials next time, unless you want to listen for another 10 minutes, but I think that you don't. So, okay, I'm going to stop there and take questions.